This is the second part of the video, all about total internal reflection. So, in what we've done so far, we've seen total internal reflection, in fact, how we can work out the critical angle. Now, where we can use this and revolution is Christmas trees. And I got lovely Christmas trees I brought out in the lab, but sadly, I can't show it to you. So I got a picture of a Christmas tree instead. I know, you're appreciating it, aren't you? So when you look at the Christmas tree like this, it's an optical fiber one. And you can see the light coming out, and the light seems to be trapped in these all little optical fibers. So what you've got is a very thin piece of material which light can go through in case of blue light here. And there you haven't got it, but normally you've got a cladding around the outside. So this is an optical fiber, and how it actually works is, as light comes in here, first of all, we've got a little refraction happening there because it's going air into that material, whatever it is. But then when it goes here, it's trying to leave the material. So what you've got to do is you go on the pen here, is you've got on your N1 and you've got your N2. I really wanted it black, but never mind. It's going from N1 to N2. Remember the conditions before for critical angle is we're going from here, where we got your glass going to air. It's got to bend away from the normal. Eventually you get like this. Therefore, you've got to have your N1 greater than N2. So what you do is make the critical angle, the refractive index of N2 is going to be less. In that case, then, you will find the light comes in, you get TIR. Now, it normally is above the critical angle because it's narrow. And because it's narrow, it makes this angle here pretty big, so you meet the condition where the critical angle of incidence here, okay, is going to be greater than that critical angle, therefore you get TIR, and that's why these optical fibers are quite narrow. The reason why you got a cladding on here, and they do ask about this, is because when you've got optical fibers used in digital technology, like in phone lines, etc., imagine you've got shed loads of, you got lots and lots of optical fibers inside, all bunched together. Now, if they then all these tubes touched each other, you get something called crossover. In other words, this is matching refractive index, therefore the light can go from that one through to this one and cross over from the optical fiber. And stop that happening, you normally have a cladding here, basically stops the light jumping between optical fiber, and that's the whole function of the cladding. Now, other things that mentioned in the book is, first of all, is multipath dispersion. Now, what is meant by multipath dispersion is you've got here your tube going, this is your optical fiber, and I go cladding on the outside here and here, but at the moment, let's say the light is bouncing in back and forth like this. Well, as light comes through, it could go through a direct line like that, or it can go up and down, reflecting like this, and we've got total internal reflection here, here, and here. Now, if you really think about it, isn't this light doing this going to travel a lot longer path than the light going through the center here? In other words, what happens is you get something called pulse broadening. So digital technology, it works like this. This is a 0, that is a 1, and that is a 0. In other words, digital only works noughts and ones. Therefore, when the beam goes up, you got a 1, and the beam's on, you got a 0. What happens then, as it goes through, because this one is traveling longer than that one, can you see here the width of that pulse suddenly is made wider. Now, when it's made wider, you get something called broadening happening. And you don't really want that to happen. It causes a problem with the digital signal coming out. So to minimize that, and this is why you make your tube narrow, is the fact what you do then is you make this narrow as possible. Therefore, I've only made it that sort of width. Therefore, the path different, the distance the wave is going to travel is going to be less. Therefore, the pulsing happens less, because you're going to have, it's going up and down, but the distance further it travels going up and down only up to here, the damn sight less than it was going to there. And that's why I use it. Now, spectral dispersion, also you've seen is the refractive index is dependent on the wavelength. Now, you'll find this in your book, and again, it mentioned this all the way through. You've got it in on page 194, And because the refractive index is dependent on wavelength, what can happen is as the light comes through, again, the critical angle will change slightly depending on the wavelength of the light. Therefore, what we find in digital technology, we'd use something which we mention a lot in the future, is called monochromatic. Now, what I mean by monochromatic is only going to have one wavelength. Therefore, a lot of the time we use this digital technology, what we do is we actually use a laser. And laser uses light, which is monochromatic, has one wavelength, whatever it is, red, blue, green. And therefore, that avoids the problem with spectral dispersion. So, I'm going to leave you to research this, is find out about endoscopes. You can do that yourself. Endoscopes, great piece of technology. What they use optical fibers to see inside bodies. Yeah, have a look at that yourself and find out how an endoscope works using optical fibers, and also find out as well how we can actually use optical fibers in communication. So what I've just covered all the way through is I've now been through the conditions of a total internal reflection. You know how to calculate from the critical angle from the refractive index. I mentioned why you've got cladding there, and the structure of an optical fiber. I mentioned about multipath dispersion, and I'll leave you to find out how it's used in communication and also endoscopes. Hope you enjoyed it.